It gives me pleasure to introduce our speaker today, Professor Terry Rudolph. Um, Terry is co-founder and chief architect at PsiQuantum, and he invented the computing approach that forms the basis of PsiQuantum's quantum computer design. He finished his PhD in theoretical quantum optics, and then he was at the University of Toronto in Bell Labs, then moved on to Imperial College in 2003. In 2016, he founded PsiQuantum, and with that, I'll hand it over to Terry. Thanks.
Hey folks, it's great to be here. I should extend my thanks to Kate and David and CQE for inviting me, but they didn't invite me. They actually invited Jeremy O'Brien, our CEO, and unfortunately our marketing guy said, look, this venue's too nice for Jeremy. He's just not good looking enough. And so I had to step in. I really want to just tell you a bit today about, what we're doing, where we're at in our progress, how we're doing it, and why we think this is the way to go. PsiQuantum, as you possibly know, is one of the largest hardware quantum computing efforts on the planet. We've been going since the end of 2016. And, I'm a quantum physicist. There's a small number now of quantum physicists in the team. But a large number of our technical people come from semiconductor manufacturing, from electronics packaging. Increasingly, as we're building bigger and bigger systems, we're hiring people from the oil and gas industry and so on. It's really a very large machine that we're building. And I think a natural question you might ask is, why is all this effort going into quantum computing? Maybe you've got a friend who works at McKinsey or at a BCG, and you go to them and you say, why is all this effort, like all this money, people's time, lots of people going into it? And what that management consultant friend would tell you is something like this. They would say, look, there's a whole bunch of modern technologies whose underpinnings in chemistry and physics and mathematics are going to be revolutionized if we can build a quantum computer. And that is true, but it actually hides some real challenges that even once we have a quantum computer, how to unlock this kind of potential is very challenging. And the reason is that quantum computers are really fundamentally different. The logic is different. We can't just take, the standard classical logic of classical computation. There's subtleties to do with the fact that in a quantum computer, CPU and memory are equally expensive. That's not true in a classical computer. And, frankly, writing quantum algorithms, despite my amazing good looks, I'm over 50 years old. And I'll tell you, back when I was a kid learning how to program a quantum computer, a classical computer, you had to really write machine code. You had to optimize when you're programming a Commodore 64 or whatever. And the same will be true of quantum computing. To understand how we're going to get the potential of the quantum computer out, we have to do the equivalent of the machine code, and to design these quantum algorithms can really only be done in conjunction with the people building the quantum computer, i.e. with us. And so we do work with a lot of organizations, both commercially and in the government sector, on exactly this problem. Okay, so we have many partnerships across the US. We have, some are to do with building a machine. Many are to do with just how we extract this algorithmic value from the machine once it's built. We have to do this resource counting analysis. It's a large, tricky problem. Yesterday, we announced a global collaboration with Lockheed. We've been working with them already for a few years on just how to unlock these applications in national security, defense, aerospace, and so on. And to the exciting announcement that we just had from Undersecretary Gill, we've been working with Argonne as a partner in that QNX center, and we're very happy that that's going to continue. So, yeah, getting out this potential, you know, one of the mistakes you made was talk to a management consultant. You shouldn't talk to people, they don't know anything. What you should do is go to a professor in a computer science department, there's many of them, and they'll say things to you like, look, dummy, because that's how professors talk. They'll say, the mistake that you're making is that you're thinking that quantum computers are going to be a little bit like all the hype you hear about AI in classical computers, right? All of those problems that I put there, you're hearing the same things about AI. Oh, it's going to revolutionize chemistry and biology and farm and transport and so on. But actually, quantum computers the things that are solvable with a reasonably sized quantum computer is like a strictly larger, it's a bit hard to see on this thing, set of things than the things that are solvable with regular computers. And we computer science professors can prove this mathematically, or provide you very strong evidence mathematically. And what happened was everyone sort of thought that the things solvable with regular computers fell into this little box, but actually AI came along and it sort of expanded that box, but it didn't go outside of that box. And AI cannot, because AI is based on classical computers. And so quantum computers, very exciting, can't do everything. There's going to be things that they can't do. But quantum computers are a strictly more powerful machine. And of course, that professor is also correct. But as someone trying to build a quantum computer, I can tell you the following, which is that even if there is a problem that can be solved with AI or a classical computer, the person building this expensive and difficult quantum computer does not want to tackle that problem, right? These should be complementary synergistic technologies. They're not competing technologies. And so the sort of workflow that I have in mind of how to make quantum computers work together with AI goes something like this, right? So I'm going to pick an example from biology or chemistry. Imagine you have some functionality, some molecule that you want to create. There's a lot of potential with AI and conventional machine learning to just train the classical computer with a whole bunch of experimental data to learn chemistry and to help you design this molecule. But of course, that data is very hardly won primarily from experiment, right? Because we can't solve these basic equations. So you've got to go to a wet lab, hire people. People are expensive and unreliable, generate a whole bunch of data, and then train your machine learning system. So one place for a quantum computer is simply just to generate high precision, reliable data that you then use to train your classical AI. And this is a very obvious use case. I think there's some interesting things here in that the quantum computer, of course, isn't limited like the person in a lab is limited by what things, temperatures, pressures, chemicals, and so on, solutes they have. A quantum computer can actually generate data that's not even possible to generate in a lab. And I think it's sort of exciting to imagine that that will then allow the AI to sort of understand the space of chemistry much more precisely and much faster. It's a bit of a speculation. Either way, what we know is that we will never get just a single answer out of one of these AIs. Typically, we get hundreds or thousands of potential molecules, things that maybe are a candidate for solving whatever problem you have. And then, of course, your next challenge is you've then got to synthesize all those molecules and test them, which you could do again in a wet lab. But this, again, is a slow, expensive process. And so, again, I think a quantum computer is going to come along and say, I'm going to do this filtering for you of these candidates. And that, I think, is a very strong possible first use for quantum computers. Right? There's a small number of molecules here. So this is the way I sort of view this workflow between sort of AI and quantum computing. Now, that all sounds good, but obviously we don't have this quantum computer yet. And so why? Well, the answer you heard a little bit already is that the errors that we have in our qubits, in our quantum bits, add up if we don't do good error correction until after only a few hundred operations, we are essentially getting noise out of the machine. Okay. And so the way to deal with that is to do error correction, fault tolerance. We need to get to the point of doing billions of operations. And it's sort of been known theoretically that this was possible And when we founded PsiQuantum, we charged around Silicon Valley trying to say to people, look, let's just try and build a big machine that can do this fault tolerance. We need 1 million qubits. We literally went around, our mantra was, we need 1 million qubits. And all those VCs said things to us like, yeah, but look at IBM and Google. They got 100 qubits and they think that's okay. And that tells you something about VCs. And eventually, the world did come around once people saw that you really can't do much with just a few hundred qubits. And so now it's sort of, you don't have to listen to me. What do I know? You can listen to these people who know even less quantum physics than me, but who all support massive efforts at building a quantum computer. And the reason they support those big efforts is that they spent those years that we've been trying to get to building 1 million qubits, buggering around with 100 qubits and not getting anything done. And so now they all say, yeah, we need 1 million qubits. We've got to do fault tolerance. We've got to do all this stuff. Okay, so great. Everyone's agreed. You've got to build a big machine. You need fault tolerance and so on. What are the challenges to doing that? Well, everyone can make nice qubits. The real challenges to scaling to a big machine are essentially these 4 things. You need to be able to build billion component machines. You need to cool them. Every technology needs cooling one way or the other. You need modularity and connectivity, and you need to deal with classical control, classical side logic and electronics and so on. So these are the challenges. I'm going to talk a little bit about the first 2. Here is the sort of overview of PsiQuantum's photonic quantum computing approach. This slide really captures 10 orders of magnitude, or at least in scale. I'm talking about components down here on silicon chips all the way up to the final machine. The stuff on the top is schematic. The stuff on the bottom is actual stuff that's been built. But if you want to understand the very basics of how does a photonic quantum computer work, what's kind of cool is that it's very easy to demonstrate yourself tonight. When you sit in your living room and you put a lamp on next to you, and you look at that partial reflection of yourself in a window, you see like part of you's reflected and some other light from the outside. That's actually a quantum effect, and it's the same quantum effect that we are using to build a photonic quantum computer. We have a source of light. So for you, that source was a lamp. We use miniature sources that we pump with lasers, make nice clean photons. Then the photons propagate, and when the photon in your living room hits the window, it actually goes into a quantum superposition of going both through the window and bouncing back off the window. So it's sort of in this weird quantum state of sort of simultaneously being on the other side, outside, and inside your house. And then it hits your eye, which is a photon detector, and your eye is not a bad photon detector. And that collapses the quantum wave function and does a whole bunch of kind of funky stuff. And the only part of the story that we need as well is a switch. So in our quantum computer is built very much like that, and it would be a bit big if we tried to build it out of living rooms. We also need a switch, which is a little bit like a mirror on a stick. If you did that, you can go do some quantum computing tonight, apply for some grants. You might get a few $1 million, who knows. But that's what we do. We just build these components, these very simple, basic components, but we do them to incredibly high precision over and over again, design these things to make them as low noise and to make them as manufacturable and identical to each other as possible. So that's how our machine works. I'm going to tell you a little bit about the manufacturing. So this is Fab 8, which is Global Foundry's premier facility. This is a place that makes laptops and cell phones, and we've been working with them for years to stand up processors here. These robots that you see here, there's 11 of these robots, 30-odd chambers, just dedicated to manufacturing PsiQuantum's chips. And we build our wafers there. Each wafer comes in it's like the size of a pizza, 300 millimeters. It takes about 900 process steps just to make these chips, 40 mask layers and so on. These are complicated chips, but we're very happy that we now have a dedicated team here. So one of my other co-founders is in this picture, but he's also not good looking enough to be here, so we just covered him up. But we now have this kind of feature complete platform for manufacturing our chips. And so we're very excited by that because the quality of what we can get out of the process as a global founder is extremely high. Okay. This I'll just show you is a optical switch. I've just got this here to show you that it's also packaging that matters. Okay, the chips are made, but then the chips have to be connected with electronics, optical fibers that come in and out. So the machine is not just the wafer of chips. It's actually something which is packaged chips that all then get connected to each other. So this is a switch. This is an 8-port switch. We now make 64-port switches. But yeah, it gives you a sense of what it is that we're building at the microscopic scale. Now, what I really want you to understand, though, is that the machine, as we're building it at the macroscopic scale, is very big. Okay, this thing really looks like a supercomputer or a data center. It's a big thing. One of the big features is something that's not quantum. It's like we need to cool down these chips. And the reason that we need to cool down these chips is that the single photon detectors, the things that are the equivalent of your eye in our machine, are built from small pieces of a superconductor that sort of sits on top of a waveguide. So the photon travels along. This is just like a ditch cut into the silicon. And then this detector absorbs the photon, gets hot, that creates an electrical signal. But unfortunately, it needs to be cooled down to 3 Kelvin, which sounds cold, but if you're an experimental physicist, this is very warm compared to the technologies of, say, superconducting qubits, but it's still cold. And we're serious about building a very big machine, and so we need to be able to cool down millions to billions of these detectors, or billions of them, eventually. So for that, we need liquid helium to get down to this kind of temperature. But fortunately, building big cooling facilities of liquid helium has already been done. So this is up the road from us in Palo Alto. This is the Stanford Linear Accelerator. This is their cryogenic power plant. It's about 18 kilowatts of liquid helium cooling. And they gave us a corner, because the DOE are such kind people, they gave us a corner to assemble a prototype cryostat. And this has been really revolutionary for us to be able to do this and test this thing. So it sits in the corner of this cryo plant. We're only taking a tiny piece of their liquid helium. The rest of it's going into the particle accelerator because they're updating it to some kind of free electron laser. But yeah, that's essentially the size of cryoplant that we need to build our machine. So here's a schematic of the machine from start to finish. This is something we show our employees in the company to give them a sense of what it is that we're building. So we have these wafers. The wafers are broken up into chips. There's the sources and detectors and components on the chips. The chips get glued to a copper backplane down which this liquid helium cools it. So that's all the kind of quantum-y stuff of the machine in one of these cryostats. And then there's a whole bunch of other stuff on the side, like lasers, control electronics, all the stuff that kind of makes one sort of basic unit of the quantum computer. And then the final machine is sort of order of 100 of those things. Okay. We're talking about a very large manufacturing project that we're engaged in. So that project, where are we at? I said I want to give you a sense of what it is we got to do and where are we at. I've just shown you like that one cryostat at the Stanford Linear Accelerator. Right now, we just took over a facility in Milpitas near San Jose, in which there's going to be a room of sort of 3 or a few more cryostats, and that's what it currently looks like. So it's obviously a bit of a mess, but progress is actually very rapid on that at the moment. And so that facility will be several such similar cryostats linked together. This is a little animation of how that facility is being fitted out right now. And so that's what we're at. That's where we're up to, is building this stuff in the Bay Area, like in San Jose. And what I'm here to tell you about is kind of what we're going to do in Chicago. So that sort of sets the scene for what we're now going to be doing in Chicago. Okay, before I sort of show you what we're going to do in terms of the building site, I should add that we're really happy and excited to be engaged in many different ways with different parts of this Chicago quantum ecosystem, in education, but also in things like this. I talked about the difficulty of writing quantum algorithms that do real resource accounting. We've had 7 years of making a tool that we call Construct. This is how we do it internally in the company, and we're making it available to various facilities in the Chicago area. Okay, so where are we at with actually building the machine in Chicago? Well, a few weeks ago, we had a groundbreaking. This is the quantum computer. It's a pile of fake sand. This is Jeremy, who should be giving this talk. You see why we didn't let him come. They cut me off here because they were like, yeah, you'll just steal the show. So I'm like around the corner here somewhere. And this, of course, is Governor Pritzker, who's been a big supporter of this whole thing from the start. So yeah, here we were shoveling some fake sand, but what we're building on this site, so where that was, if you don't know, is on the old US Steel site in South Chicago. This is what it will look like in the end once this full IQMP is fitted out. In terms of what we're doing, the first thing that we're doing is going from that 3 cabinet, that 3 cryostat thing that you saw, to one that's sort of on the order of tens of such cryostats. And so that's what's going to be in this first building. So if you go anytime soon and look at it, you'll see in there. And then this here is what the final quantum computer will look like in terms of its full deployment. It's like a very large thing. Okay, that's basically it. I've run out of time. I wanted to tell you kind of where we're at. But this, much more interesting than watching politicians shovel sand, are the actual trucks going on. This is a very recent little video showing you that this stuff really is underway. And so, somehow when I see something like this, it's just incredibly exciting because I see that the long poles in the tent are now finally being built, that large-scale stuff that we need in order to get this whole machine going. So I'll leave it at that. Thank you.
Thank you, Terry. Floor is open for questions.
Hi, I'm a reporter at the Wall Street Journal, and wondering why you chose the Chicago site. What about it was attractive? And also your Forever Impossible box from your slide. What do you put in that box, just out of curiosity? Which problems?
Oh, okay. So the Forever Impossible box, I mean, this is, in computer science, there are problems that we don't believe that any size quantum computer or any size classical computer, what those boxes refer to are reasonably sized machines. So the box that sort of has quantum computing, is a machine where even if that only a quantum computer can do, it's sort of saying, look, there's a machine, there's a problem that a small quantum computer can do that even if I turn like every atom in the solar system into a classical computer, it won't be able to solve that problem. So there's some problems like that. But then there are problems that we say, look, even if I turn all atoms in the universe into a quantum computer, they still won't be able to solve those problems. So this is a very, computer science has a very intricate hierarchy of problems. And it's not as trivial. And this is one of the most annoying things about the hype of quantum computing, AI, and so on, is that these nuances get lost, right? Like, fortunately, the kind of problems that we can get that have a large amount of impact do fall within the remit of quantum computing, things in quantum chemistry, biology, and solving differential equations, all of these things. But yeah, there are problems which no one will ever solve, no matter whether it's a quantum or classical computer. And then, why Chicago? There's a very, very strong ecosystem here already. I've been working for many years with people at UIUC since early in my career. But the support in Illinois for this venture, we have to have a US site for this thing. And the support we got from here was incredible. And so, we're very grateful for that.
Hi, Julia Galli, University of Chicago and Argonne National Lab. I have 2 questions. One is addressing the problem of quantum supremacy really the right thing to do? In the sense that, I've worked in classical computer simulation for many years, and there has been, this discussion about scaling of algorithm. And scaling is good, right? You can have order n instead of order n cubed, but the prefactor also matters. Mm-hmm. So at the end, shall we be talking about quantum supremacy, or also what we can do that really will change science and society? Second question is, are the problems that you hinted at in chemistry and biology really the major problem that we should be thinking of, or are there other problems that you have in mind?
So those, okay, so let me answer the second one first. The reason why I singled out those ones is that the first quantum computers are going to be small. You know, it's going to be like using a Commodore 64 instead of a whatever Cray. And so we're just picking the problems for which we have good reason to believe that a small algorithm can still outperform even the largest classical HPCs, right? So that's very much a problem specific. If there was a different problem, we'd pick a different one. It's got nothing to do with the fact that the machine is a quantum computer. It's almost coincidence that, you know, we're talking about a quantum problem on a quantum computer. To your first question, so, you know, we as a company from day one said we're not interested in quantum supremacy. There's a sort of technical definition of quantum supremacy. It's a bit like, I don't know, having a calculator when you want a programmable computer or something. We were just never interested in it. We've only ever been interested in, can we solve some problems that are useful, that cannot be solved with any amount of sort of classical HPC. And I think, you know, most of the community has come around to that, and if they haven't, they will soon. Like, I just think supremacy is just not an interesting thing, and I'm certainly not interested. I'm a scientist, you know. Like, so.
Hi, thank you. I want to talk a little bit about the cryo system that you're using. So it looks like
this is like the very furthest away thing from what, you know, I'm a quantum guy and there's some massive pile of pipes and things. So yeah.
Yeah. I just noticed one of the major energy costs of this whole thing is getting it down to the Kelvin or millikelvin temperatures that you need. But I look at like IBM system, like they're all using that chandelier system. I see you guys are using the cabinet system.
This is because we don't go to millikelvin. So it's a completely different cooling technology. So the cooling technology that we use really is the same as the one at SLAC or, you know, many other particle accelerators and other places. Like it is essentially that cryo plant. You can go on Amazon and order it for $100 million, right? Like it's just order it. So we don't have to invent a new cooling technology, which I think all of the places, you know, all the technologies that are using sort of dilution refrigerators, maybe they can build one 10 times bigger, maybe they can build one 100 times bigger, but, you know, they need a 10,000 times bigger system, and this is why they're going to network and do other things. So, yeah, these are just very different cooling technologies.
Thank you. My name is Michelle. I'm a student at UW-Madison. So again, going back to that visual you had with the problems, the classical problems and the quantum problems, it looked like the quantum problem box encapsulated the classical problem box. And I wanted to expand on that a little bit because my understanding was that quantum computers aren't necessarily suited to solve a lot of classical problems either. So I just wanted to see why you arranged it that way.
My advice to you as a student is like, things like that are the sorts of things that a computer science professor says, right? In theory, a quantum computer does encapsulate, like, you know, if you have a universal quantum computer, you can definitely solve, in principle, every problem that a classical computer can solve on the quantum computer. You would be foolish to do it because of the cost of building such a big quantum computer is just prohibitive. And we certainly don't know how to get to that yet. And maybe one day we will, maybe one day we won't. So really, this is why I was trying to say, you're going to leave each technology to do the thing that it does best. And the quantum computer, at least, you know, there will be some problems that are not related to AI, but the things that are sort of related to AI that I can see were the things I was showing, where you generate synthetic data or use it to evaluate performance of things. But yeah, the idea that someone will start using, you know, a quantum computer to make a better Minecraft or something, that fills me with horror.
Thank you for the great talk. Yeah, I think an impossible problem would be like, say, the halting problem, for example.
Yeah.
I just sorry, it's a specific question, but with it being new, you mentioned a construct. I wonder if you could maybe tell us a little bit more about that. I think you guys have a workshop scheduled later this week.
Yeah, so when we started the company, we didn't think about the fact that we really were going to need to also build an algorithms and applications team to work out, like, how are we going to extract all the value from our machine. We sort of thought, and I think this misconception does still exist in the community, that you could do algorithms independently from the hardware. But it turns out You really can't. And anyone who tells you they are is just full of nonsense. The optimization really does depend on the hardware. Like, you know, what gates are easy, what gates are hard, what code you're using, how you're, just the resource costing. And so we built a very large tool set we built an algorithms team. I think it's one of the largest in the world now. And then they, in conjunction with a whole bunch of software engineers, have spent, 6-7 years now building a suite of tools. And then some of those tools have now been sort of packaged up to make them a bit more user-friendly. And we're now trying to open it up and train people on how to use those things so that they can see whether, basically what everyone wants to know is, for the particular type of use case I'm interested in, what generation of quantum computer, how far away are we from a machine that's big enough to run that problem? And that is actually a very challenging problem to solve. It takes, multiple people running these kinds of tools, understanding the problem, because there's so many little simplifications you got to do. And the quantum computer is just going to have, the first machine will have a certain size. And if your problem doesn't fit in on that, you're going to have to wait for the next generation until we expand it out and put it. So that kind of thing, I think, it's great for students to learn quantum stuff because it's got so many different aspects in it. And for us, it's now at the point where we're sort of big enough and have the resources. For many years, we didn't open up because we're not an IBM or Google. We're a small team trying to get the machine built. Building the machine far more important to us than promoting it. And so we sort of had different motivations, but we are now big enough that we have opened a lot of this stuff up. And I encourage you to look at it. It'd be fun.
Hi. So I have a quick question and a small remark, quick remark. So first, the remark just about the box, or at least training the data on wet lab data. I just want to note that the quantum chemistry has been a field that has been evolving for very, very many decades, and the accuracy that they can get is quite impressive. And you don't need to train your models only on synthetic, on wet lab data. There is plenty of very, very accurate data that that quantum computers cannot really reach that level of accuracy. But related to that,
not yet.
Yeah, but related to that, we know that the software stack, so all the presentation from every company that makes quantum computers, they talk a lot about the hardware, but the software is kind of put under the rug. And we know that this is one of the biggest issues that is going to be there, because when you have, as you just mentioned now, optical quantum computers and different type of quantum computers, it's almost like every company is expecting the whole software community to build a software stack that can adapt to this general thing.
I totally agree. And I think it's sort of unavoidable because the hardware approaches are quite different and people haven't finalized what error correcting codes they're using in the gate tests and the ways they're going to do certain things. And I think that was true in the early days of classical computing. And I think we just have to accept that that's the way it's going to be until it's really clear what is the sort of right approach. I think that's really unavoidable.
But there is no push or attempt from all the people who make quantum computers to try to include a little bit more software engineers or computer scientists to be able to at least find some finality or some common background for everyone.
We do. I think there is, and it's a challenging problem because obviously, we're focused on let's just try and get our particular machine and software and so on running. But I think something, and so this, I'll just finish with this as sort of a philosophical, historical point. I don't believe we have any clue really what the power of quantum computing software will be, because we don't have the quantum computer to test our ideas at the moment. The situation we're in now is it's like Turing, before there were classical computers. Turing got a pen and paper and he wrote out the rules for the Turing machine and he moved it around. And using a classical computer to try and help you analyze a quantum computer is as bad as Turing with a pen and paper trying to work out what classical HPC, it's inconceivable Turing would have invented Instagram or whatever you think is important by hand on a piece of paper. And we're in the same situation with quantum computers. It's inconceivable. We need, software developers need the machine to go, I'm going to test this idea. I'm going to see, does this Monte Carlo thing converge? Does this whatever? You try it, you run it, you see, you do some sanity checks. That's what real programming on a quantum computer will be one day. And until we have a big enough quantum computer and the access capacity that someone will let us do that, I don't think we have really any clue what the sort of true potential for quantum algorithms is.
Okay, thanks. Yeah, thanks for the opportunity. And thanks for the talk. So Joaquin Chung from Argonne National Lab. So I have a question based on the remark of the colleague about the accuracy of the simulation from wet labs. So based on the throughput of state-of-the-art systems like that, for generating the synthetic data and then for synthesizing the solution, do you have an estimate of like what, and hopefully this question is not too in the weeds, but do you have an estimate of what could be the speed up of the quantum computer?
I honestly don't, but we have people, like a small team whose sole job is that problem, and I can connect you with them. And I mean, with the relationship we have with Argonne, you should be talking with them. But yeah, I'm the wrong person to answer that. Sorry.
This is Yasin from Governors University. I wanted to ask you, what impact do you think this facility is going to be on the workforce? Obviously, this project is going to go fast, and there's going to be a gap. So what do you recommend in terms of skills to teach our, especially for the academic institutions, to teach?
So okay, this is not an official PsiQuantum answer. This is just Terry. Okay. I think it's ridiculous we don't teach quantum mechanics in high school, because you don't need calculus to learn quantum mechanics. It's linear algebra, it's vectors. We teach vectors for classical mechanics. It's multiplied by matrices. You can get Python to do it. And so, I feel like people coming into first year at university right now, quantum is just like, they've probably got a bit of history and, some Schrodinger cat nonsense, but like they got a very vague thing, which they could have had an actual technical underpinning even in high school. So, my contention would be you should, academic, like universities, and I've tried to push this at Imperial where I'm still a professor, we should be going hard on it in first year, not second and third. Currently, they don't really get to like hard like quantum algorithms type quantum mechanics until third year of undergrad, whereas it can definitely be started in first year, and maybe, the very basics in high school. So that, but that's just personal bias.
I know we've got a question in the back from our Zoom communication team.
Yep. So we have a question online coming from David Wu, and he's asking is 7-length long peptide prediction in the range of your system?
Sorry.
So the question reads as, is 7-length long peptide prediction in the range of your system?
Okay, again, I don't know, but we have like, on our algorithms team, there are many people who know nothing about quantum algorithms, who are purely quantum chemists and numerical quantum chemists, and they can answer those kind of questions. I definitely cannot. Like, and I should say that this is the way algorithms have to work. Quantum algorithm development is you've got to hire the people who've written already the best classical algorithms. There's no point competing with like sort of some average case classical algorithm. You hire the people who've already written code for HPCs doing the best classical algorithms, and then you bring them in and you have them talk to your quantum people, and you try and work out how can you push the envelope of what those guys are doing, but it's very far from my expertise.
So first of all, thanks for the comment on high school. I couldn't agree more with you. But I would like to add that in addition to expertise in quantum mechanics, we need more expertise in material science. And, the solution of the problems that you and many others will have on hardware also are predicated on our ability to understand and make prediction on materials and act fast on the synthesis of materials. And I think that this is underrated and should be also taught very early on in our schools.
I can take, let me take a last question then. Again, following up on what Julia mentioned, you showed the video, many devices, different materials being cooled down, very cold temperatures. That's exploring a material space that even microelectronics has not gone into. Any comments on the reliability issues that you're seeing, the challenges there at the system level?
Yeah, so then, people often ask me, because, whenever you're fundraising, what are the things that keep you awake at night? That is definitely the kind of thing where, you just don't know until you've tried to build a big system. Like building that one big cryostat, like that, it's such a de-risking thing. Of course, it doesn't feel like science in the sense of, you've changed how the photons move on the chip, but it's incredibly de-risking in terms of, the manufacturing, the yield, like we've got to glue fibers onto chips, like all of this stuff, you've got to have a robot do that, right? You can't hire a PhD student to sit there and glue 1 million fibers onto chips. So all of that kind of stuff is where the sort of large-scale risks happen. And some of them, you plan for them and you anticipate them and you work around them. And we hire people who've built, things like the Aurora, or, things that are large machines, and they can tell you all of these procedures and so on. But at the end of the day, we need that performance. There's no point having like 1 or 2 qubits that hit some fault-tolerant threshold. We need the performance of millions of these things all in this final stack machine. And that is the kind of frontier of what we're doing. And, I think until we actually do it, we don't fully know. So that is absolutely the sort of, that's why I was trying to show you the scale of where we're at. It's that kind of scale of thing, which is super critical for us right now.
Right. So let's thank the speaker again for an excellent talk. Excellent talk.